So here we have our open top box. We're trying to decide how much to cut out of the corners. We're going to come up with a volume equation. And so before we can do that, we need the dimensions of this box, all three of them. So we've got, it was 8 inches wide. If I cut out X inches from each side, so if I cut out 1 inch, I'd be taking off a 1 and a 1 here and here, bringing it down to 6. But an expression that represents the amount that I'm cutting off of each end is 8 minus 2x. And then down here I would have 12 inches, but I'm taking out 2 x's from the length as well. So it's 12 minus 2x. And then when I fold up the tabs right here, 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 and here, that gives me a height of x. So if volume of a prism is length times width times height, then I've got volume equals 12 minus 2x times 8 minus 2x times x. And that's my cubic polynomial. Let's go ahead and multiply it out here. So we've got 96, and then this will be negative 16 minus 24, so it's negative 40x. And then minus 4x squared, and then we're going to distribute the x plus 4x squared down, and then distribute the x. When I distribute the x, I'll have the following cubic. Let's turn it around here. So 4x cubed minus 40x squared plus 96x. There's my volume equation. It's a nice cubic polynomial. And to find the values x to cut out of the corners to maximize the volume of this open top box, I need to take the derivative of this thing and set it equal to 0. Let's get a domain on this first of all. What's the domain going to be here? It does have to be greater than 0. They'll happen. And then we got to think a little bit more about this one. You know, I could cut 1 inch out. I could cut 2 inches out, 3. If I cut 4 inches out, I no longer have any width, right? If I cut 4 inches out, the width would be 0. So it's 0 to 4, open. And so somewhere between 0 and 4, we tested 1 and 2 was a little better than 1. But somewhere between 0 and 4, we have dimensions to cut out of the corners that would maximize it. So, do you understand the problem in terms of what we're doing? Setup okay? No, they all kind of follow the same pattern. So V prime equals 12x squared minus 80x plus 96. Set that equal to 0. You could even do the second derivative now. I'm going to use the second derivative test since it's a nice polynomial. So I've got 24x minus 80. But I got 12x squared minus 80x plus 96. I'm going to set that equal to 0. And I'm going to solve. Can we simplify it a little bit? What can we take out of it? Four out of it. Yeah. So divide through by 4. We got 0 equals 3x squared minus 20x plus 24. And then the question is, can it be factored? If it can't be factored, we got to use the quadratic formula on it. So are there factors of 72 that add equal negative 20? Sometimes you might want to just decide to go straight to the quadratic formula. I mean, it's kind of one of those things that mess with it. You remember the quick test with the quadratic formula? Testing the discriminant? What are we looking for under the radical? Yeah. So it just, yeah, I was looking to see if it's a whole, if we can take the square root of it. It's a perfect square. So x equals opposite of b, which is 20, plus or minus square root. And when I say plus or minus, I'm just solving the quadratic. One of these isn't going to work. It's going to give us a negative value. So we've got negative 20 squared. That's 400 minus 4 times 3 times 24 over 2 times 3. What's happening here? Let's see, 80, 96. It's like 12 short of 300, so 288. So 400 minus 288. What's that? 400 minus 288. That's 112. 112. So it wasn't going to be factorable. What decimal value do you get for this? And let's just write down just the plus one, because if I subtract off the 100 square root, 112, let's see, does the minus one work actually? I think that one might be possible. Yeah, I think both of them could work. One of them is actually bigger than 4, I think. All right, so what are my two values? We have a calculator handy, a decimal on it. 20 plus square root of 112 over 6, what do you get? James, you got it for us? Almost. Like 5/3 is one of them. It's like 1 and 2/3 is one. And the other one is like, the other one's over 4. Okay, yeah, right around 1 2/3, yeah, 1.569. Okay, so about 1.6, 1.569, or it's 5 point something or other. Okay, so we can toss out that one. So our only candidate is the 1.569. So to test to see if that's truly a max, I can plug it in to V double prime there. And what happens when I plug that into V double prime? V double prime of 1.569. Is that going to be positive or negative? Negative. So it's less than 0. So I've got this picture happening, right? So x equals 1.569 maximizes volume. So on the free response, on the exam, they want you to take it to 3 decimal places here. I know that we need to do that here, but that's kind of like the general rule on these calculator allowed ones. So, but we have about 1.6, and the volume that we get with about 1.6, once again I'm going to use 1.6, not 1.569, but the volume we get is, we just plug it in, 12 minus 2 times 1.6, 8 minus 2 times 1.6, and then times 1.6. And I get my volume. So 1.569, and we're, 1.569, the calculator would have done it for us. Second, calculate max. Remember that feature. With calculus, we've got it pretty accurately here to 3 decimal places, 1.569. And then the volume that it gives us when we plug that in, anybody have that? Exercise left for the reader then. But that's it. So you got your volume for a given cutout.
67.58.
Inches cubed. Right. So pretty standard problem. That's problem number 7. And then they have one other. They might do one where they add the lid in part of the material, and so you can give an explanation on that as well. So there's a couple of these. 7. All right. Questions on that? Put it down. Everybody else still writing? Okay. So you've been asked, this is example 5, you've been asked to design a 1-liter oil can shaped like a right circular cylinder. This is, once again, this is one that's like, what I've done on some of these is taken old pre-responses and added them to the examples. This is the type of thing you might see on there. They would have other parts to it. They wouldn't just ask this one thing. They might add in some kind of rate of change, like they might be filling it with water or something like that. They'd add something else in. But you've been asked to design a 1-liter oil can shaped like a right circular cylinder. So what dimensions use the least material? So this time, instead of finding the value x that maximizes the volume, you're finding, in this case, the values r and h that minimize the surface area of the material you're using when it's all laid out flat. If you were to think about, what is this thing made up of? It's made up of 2 circles, right? 2 circles and then 1 rectangle. It's this whole idea. You've probably seen it before. Here's a right circular cylinder. It's just a piece of paper rolled up is a good model for that. You got 2 circles, top and bottom. And then the circumference of the circle becomes this edge, the length of it. And there's the height. So remember, they need to give us 2 equations so that we can solve one equation for a letter and plug it into the other one. So you always have 2 equations, so expect that. Think about what the 2 equations are. Even if they don't explicitly give them to you, there is some other relationship there. It might be a Pythagorean relationship. It might be a perimeter equation that you're plugging into an area type of thing. But there's typically 2 equations. So here they tell us that the volume of this thing has to be 1 liter or 1,000 cubic centimeters. So we're going to go with the cubic centimeter. And the volume formula for this, they would give it to you, but it's just pi r squared, that's the circle on the bottom, times the height. It's like a bunch of circular discs stacked up to a certain height. So you think of the volume that way as a bunch of circular discs stacked up to a certain height. So we got pi r squared equals 1,000. That's our volume equation. And we're going to actually take some version of this volume equation and plug it in down here. So surface area of a can, once again, they would give that to you. I'm showing you in the picture here where it comes from. It's 2 pi r squared plus 2 pi r h, which is the area of that rectangle. When you take and fold this thing out. So I'll let you write all that down. But that's the setup. We're going to minimize this area, surface area equation. We want minimum surface area for maximum volume. So somewhere in here, we've got to, I'll give you the hints on here. We're going to substitute for h. So in this case, it's probably easiest to just solve for h. I don't really want to solve for r. Plug it in for h. It'd be easier to solve for h. Plug it in. So solving for h looks like this. It's h equals 1,000 divided by pi r squared. So 1,000 divided by pi r squared is going to go in for h in my surface area equation. So my new surface area equation is A equals 2 pi r squared plus 2 pi r, and then in place of h I've got 1,000 over pi r squared. And it's going to be helpful to simplify this. As a matter of fact, I want that second term in terms of a negative power. I think that'll be easier. It'll end up being like something over r to the negative 1. And then you can use the power rule on it. So we do want to simplify this, I think. It's not a polynomial, but it's at least something we can use the power rule on. The pi's cancel. One of the r's cancel. You see that? The pi's will cancel. One of the r's will cancel. We've got 2,000 r to the negative 1. So to think about that a little bit here. We have r over r squared. One of the r's cancels, leaving an r on the bottom. And each time you have one of these, you're gonna see other cylinder problems. They'll give you the same volume formula equal to a different volume. And then you'll have to find the R and the H that minimize the surface area for that given volume. So like if you're mass producing these cans, my father-in-law worked for it was Reynolds. And so they were making cans for soda cans as well as the stuff they made soda cans. And so this is the type of thing somebody calculated at one point, for this given cubic centimeter that you want of liquid, and that, what's the minimum amount of surface area you need, because when you're mass producing them, that's how you're going to save on cost. So here we go. A prime. Back this time. Here we go. Remember, pi is a constant, so we've got 4 pi r, and then this becomes minus 2,000 r to the negative 2. So it's 4 pi r. It's just using the power rule on this thing. It's minus 2,000 r to the negative 2. And as soon as we end up introducing two different terms, you're going to take one term, move it over to the other side, and cross multiply to solve. So as soon as you introduce two terms, here's what this term would look like. If I set it equal to 0 now, I've got 0 equals 4 pi r minus 2,000 over r squared. That's what that term looks like. Now I go back to changing it so that it doesn't have any negative values, because I'm not going to take the derivative again. I'm not going to use the second derivative test on this. I guess I could. I'm going to actually use the first derivative test though on this one instead to show you, to prove. I guess it's really proving that the r value we get is in fact going to minimize that formula. I'm going to prove it. We won't have any other choices, because let's think about the domain here. We should probably have that up here. Let's think about the domain. What could the domain be? Take a little more thought. Values could it be? Not real obvious with it like this. How, do you have any ideas on domain? Yeah, start here. What's the biggest the radius could be? I don't know if it's that obvious here. How could we use technology to figure it out? Take what's that?
Set pi r squared equals 0.
R squared equals 0. We could set this whole equation equals 0. Or just graph it and find where it crosses. So let's graph it. 2 pi r squared plus 2,000 r to the negative 1, 2,000 over r. If we graph it, to second pi x squared minus 2,000 divided by x. What do you think on the window on this thing? What do you guys think on the window?
Maybe plus 2,000.
What was it? Plus 2,000, yeah. So it is plus 2,000. It's going way up there. So if we zoom out here. I see nothing. All right, let's go ahead and finish this and solve for R, and then we'll have an idea of kind of where we're landing here. So if I flop this one over here, 2,000 over R squared equals 4 pi R. Let's go ahead and solve for R, and then we'll go back to our graph and think about that some more. It's going to be, so let's see, cross multiply here. I got 4 pi R cubed equals 2,000. And then R cubed equals whatever 2,000 over 4 pi is. And then R equals, so just doing the algebra here. Move that over, cross multiply, take the cubed root of each side. So whatever the cubed root of 2,000 over 4 pi is. So let's get a decimal value of that, and then we'll get a value of where kind of the neighborhood of R there. And then we'll go back and play with the window and that. So 2,000 over 4 pi, take the cube root of it, what do you get?
5.42.
5.42. So 5.4 approximately. So we've got a radius of 5.4. It turns out that's going to be the value that will minimize it. It's the only value we have. It's the only critical point. So if R is our X, let's go look at one more thing here, and then we can get our window. If I plug in 5.4 right up here, so plug in 5.4 up here, what kind of area do I get? 5.4 squared is about 25, times 2 is 50, times 3, 150. 2,000 divided by 5 is going to be about 400, right? So 150, what did I say, 150 plus 400, 650-ish, I think, was the surface there. 650, I think, was the surface there. So that gives me an idea. 550, 650, somewhere in the hundreds. So if I go to the window, X min, X is the R, so X min is 0. Let's try 10 in there, X max. X scale is 1. Y min 0. Y max, let's say 1,000 is pretty good. Graph. There it is. Okay, so now it came into the screen here. So here's our minimum right here. Okay, so here's our minimum. It's kind of a branchy looking thing, like 1 over x would look. But here's the only branch we care about is the one in the first quadrant, and there's our minimum. So yeah, in terms of a domain, in here a reasonable domain, 0 to 10 seems to cover it. So let's go back over here. Let's go back over here, and we're going to do our first derivative test on this guy. So we got R equals 5.4. Go back to our first derivative right here. So we've got interval, and the interval is going to be from 0 to 5.4. And then the other one is going to go 5.4 up to somewhere around 10-ish. 5.4 to 10. So, or you could go to infinity if you want. But those are our two different intervals, and we're going to check sine of A prime, just to prove what we're seeing on the graph, that this is in fact a minimum. R equals 5.4 is a minimum. So if I plug a value into the first derivative like 5 here, if I plug in 5, then I get a negative value. And if I plug in something like 6 or something like that, I get positive. So I'm going from negative to positive. So by the first derivative test, I know this is a mass. Okay, so it's telling me that F or A is going from negative to positive. And so by first derivative test, R equals 5.4 is a min. And they would ask you to demonstrate that you know it is a minimum value. And so to demonstrate that, you've got to use either first or second derivative test. Even though we know that on an open interval, this is the only critical point, it must be the solution. Okay. So just be aware of that. So if R equals 5.4 is a minimum, H is going to be, I'm going to go back up to the original equation here, the very original. So H will equal 1,000 over pi 5.4 squared. So Eric, you got it for us?
Yeah.
Okay. So 1,000 over pi times 5.4 squared, and we'll get our H, and that will minimize it. R equals 5.4 centimeters, and H equals
10.9.
10.9. 25, 70. Okay. 10.9 centimeters. A is min. Then you can find the surface area by plugging those in to the surface area formula. So that's minimizing. Do one more minimizing one. This next one is kind of like this poster right here. I'm creating one of these posters, and what they're going to do is you're going to try to minimize, once again, the area used, but we have a given, like, it's like a frame of a picture. It's like the picture is fixed already, and so you have to have that dimension within your poster, but we still want to minimize the area that you end up using, the amount of paper you end up using. So that's what the next one is. You've been asked to design a poster for an upcoming concert. It contains 60 square inches of printing. That's like in the center of it. It'd be like this vintage transport thing being in the center. It's like that's fixed. We can't change it. It's 60 square inches. Okay. With 3-inch margin on top and bottom and 2-inch margin on the side. So this one almost looks like a frame, except that it's a poster, so it is the whole thing. We're talking about the minimizing the entire surface area of the thing, but with that 60 square inches of printing on the inside of it. So we're leaving some border around it, unlike those posters. So it contains 60 square inches of printing with 3-inch margin on top and bottom and a 2-inch margin on the side. What dimensions will minimize the amount of paper used? So this creates another kind of complicated function. So that's part of the reason why I'm doing this. I'll show you what it looks like. So the picture there's the 60 in there, but remember we're using all this. This is not a frame, so it's not empty in the middle. We're minimizing the entire area. We've got 3-inch margins top and bottom, so 3 here, 3 here, 2 on the sides. And so we've got to write an equation based on the dimensions here and here, but we have this unknown dimension. If I were going to just pop this guy out right here, we've got, this is 60 in here. We've got maybe a base here and then a height here, but we need to have that in terms of one variable. And so we're going to use the fact that we know the inner part of that poster is 60 square inches to write an equation for h in terms of b or vice versa. It doesn't matter. So we've got this area equals base times height. And so 60 equals base times height. And so let's just say height would equal 60 over b. So height would equal 60 over b. So kind of a similar idea to that first one we did, except we were taking off the two x's. Here we're going to say this dimension right here is this 60 over b. Okay, just that red part is 60 over b. The whole dimension from here to here is going to be that 60 over b plus the 2 3's. So it's 60 over b plus 6 is that guy. So 60 over b plus 6. And then the other dimension down here, so we got, this was b, this was 60 over b. And so down here it's going to be b plus 4. The worst part of this problem, they have a couple like this within the problem set. But there's our area. We can get our area that we're going to minimize. Area equals b plus 4 times 60 over b plus 6. So we're using the fact that this inner portion is an area of 60, so I can write an expression in terms of one variable. Writing h equals 60 over b. You could have gone the other direction too. We're going to have an equation in terms of b. You could have one just as easily in terms of just h. It wouldn't matter. We're going to find the dimensions that will minimize the amount. We're just looking for the dimensions. So I'm going to go ahead and multiply this out, get our equation. Oh, we can think about. We know the domain is going to go from 0 up to 60 over b in there now. So let's see. No, it can't be. I think it's even less than that. We could probably restrict it even more. But yeah. Yeah, if we hit 60. Yeah, it can't be any more than that. Once again, you could graph it, play with the window, find out, what looks like a reasonable domain. But 0 to, it's probably going to be between 0 and, well, we have to play with some values. But 0 and 60, definitely take care of it. So distribute here. We've got the b's cancel. When you distribute there, the b's cancel. You got 60 plus 6b plus 240 over b, which I'm going to write 240 b to the negative 1, and then 4 plus 6 is 24. So I can combine a couple of those together. I've got 84 plus 6b plus 240 b to the negative 1. This is probably me again. Screw you guys. You haven't been at reaction on November 4th. What's that? Okay. It was probably my fault. All right. So do our derivative here. So a prime is equal to, that's 0 plus that's 6 minus 240 b to the negative 2 using the power rule. The b's and the 6's are not good altogether. 6 minus 240 b to the negative 2. Set it equal to 0. 240 b squared. And then take and move that over to the other side. I've got 240 over b squared equals 6. 240 over b squared equals 6. Cross multiply. Divide 6b squared equals 240. So b squared equals 40. Toss out the negative version of that. So b equals square root of 40. B equals square root of 40. And then just got to use your interval test here, going back up to a prime right here. We've got interval and sine of a prime. And we go 0 to square root of 40. And then the other one is square root of 40 up to maybe 60-ish. So, and then test those two. You could say infinity if you want. Doesn't matter. So square root of 40, just test maybe something like 1 in this first group. If I plug 1 in here, I would definitely get a negative value. So it goes from negative. Square root of 40 is about 6.5, so something like 7 if I plug 7 in here. Then I'm dividing by about 49. So now it's positive. So it goes from negative to positive. So square root of 40 is a min. And if b equals square root of 40, we can find h. H was equal to 60 divided by square root of 40. So those are the dimensions. I think they wanted the dimensions of the outer part. So that would be the inner dimensions. And so the actual, I got to go back and see what they asked for here. What dimensions will minimize the amount of paper used? Yeah, so that's a whole thing. So we've got the b plus 4 and the 60 over b plus 6. So the dimensions would be square root of 40 plus 4 by just 60 over b plus 6, right? So 60 over square root of 40 plus 6. And I would literally leave it in that form. Unless you're really going to have to go out and make this poster. Then you have to get decimal approximation. So that's it. Those are a few examples of cover. Then there's one more thing I just wanted to show you here. That'll wrap it up. One other thing, and I'll get you that quiz back tomorrow. We'll go over those other two problems too. That'll be a good thing to study for the test. When the test comes. It should be after Thanksgiving. What do you guys think we would do on something like this? You might want to jot this down. It says, what values of a and b make f of x equals x cubed plus ax squared plus bx have a local minimum at x equals 2 and a point of inflection at x equals -1? This is running through the definitions here. Kind of working a little bit backwards. We're going to find the values a and b for the original equation if x equals 2 was a minimum and x equals -1 was a point of inflection. You have an idea?
You have to go to the second derivative first because we're given one variable.
It would. And we're going to do both derivatives. So, yeah. So, when in doubt, take the derivative. So, you'd have 3x squared plus 2ax plus b And then f double prime of x would equal 6x plus 2a, and as Wyatt said, b exits out. B exits out of the problem here. And so I can go ahead and set f double prime equal to 0. So I've got 0 equals 6x plus 2a, and I really wish I had an x value. Plug in, what can we plug in for x here? Yeah, we can plug in -1. I do have an x value, right? Because I know -1 is a point of inflection, meaning the second derivative equals 0. There. So 0 equals 6 times -1 plus 2a. And then you solve for a. So what does a equal? 3, yes. If a equals 3, then we go back up to the first derivative, set the first derivative equal to 0. And what are we going to plug in for x in the first derivative? Looks like 2. So everywhere I see an x in the first derivative here, I'm going to plug in a 2. And a I know is 3. And then solve for b, and you've got it. And you know the original equation that had x equals 2 as its min, and x equals -1 as its point of inflection. So it's just using the definitions, using what we've been doing to find the original function based on information about the derivative in first and second derivatives. So let's see, it's 12. So it's 24. B equals -24. So when a equals 3 and b equals -24, you have a polynomial function with those two characteristics. If you're messing with all those area and volume functions, I'd be glad to do those. That's what the end of it. So try these problems. There's 8 of them. Between now and tomorrow. And then we'll talk about it. Yeah.
I just wanted to remind you that this is my last week before I get on here.
Okay.
So I'm wondering if I can have what I need.
I have it.
And then I wrote that
What's
my
it?
dad is using one note.
Will following please report to the attendance